Satellite communication. To communicate with a satellite high above the Earth's surface, beyond the ionosphere, we need a type of electromagnetic radiation that will pass through the ionosphere and not be refracted by it. We need the wave to travel like this, from transmitter to satellite and back to receiver. The waves that can do this are microwaves, and they're in the frequency range from 4 to 20 gigahertz. We also don't want to have to keep moving the receiving dish here on Earth, and so it's essential that the satellite stays above the same point on the Earth's surface. To do this, it must take 24 hours to orbit, as the Earth is rotating in 24 hours. Now, orbit period depends on height, and for a 24-hour orbit the satellite has to be at a height of 35,800 kilometers above the Earth's surface. We need it to have an orbit period of 24 hours, and this is called a geosynchronous or geostationary orbit. Geo relating to the Earth, so the satellite is either stationary relative to the Earth or synchronized with the Earth's orbit. It has to be directly above the equator, so all geostationary satellites, about 300 of them, are above the Earth's equator at a height of 35,800 kilometers. The signal clearly has a long way to go, but how long does it take it to go from transmission to the satellite and back to be received on Earth? Well, the height of the satellite is 35,800 kilometers. The signal has to travel there and back a total distance of 71,600 kilometers. It's easier to write this as 71,600 times 10 to the 3 meters. Less chance of making an error when you enter it into your calculator. The speed of the signal, well, it's electromagnetic radiation, so it travels at the speed of light in a vacuum, 3 times 10 to the 8 meters per second. We know that time equals distance over speed, so putting the numbers in, we get this, which comes out at 0.24 of a second, about a quarter of a second. Quite significant if you're having a conversation with somebody on a news TV broadcast, for example. We want the beam we send to the satellite to be as focused as possible, so as much energy as possible is received by the satellite. To do this, we use a parabolic reflector with a dipole at the focus. When the signal is sent up the cable, the dipole will send out a microwave signal in all directions. This is reflected from the parabolic reflector and comes out as a reasonably parallel beam. This is basically the same arrangement as a simple hand torch, where the filament of the bulb is at the focus of a parabolic reflector. When receiving the beam, we need to gather together the energy landing on a large area and bring it down to focus at a small point. This is done again using a parabolic reflector. The rays now come in to the reflector, they're focused to the dipole, the signal is then sent down the feed cable. One thing we can't avoid is spreading of the beam due to diffraction. If the beam is transmitted from a satellite dish of diameter A, it will produce a diffraction pattern like this, the same as the diffraction pattern of light sent through a single slit. We have the central maximum and the first minima here and here. Drawing a line from the dish to the first minima, this then is angle theta, and it can be shown that sine theta is equal to the wavelength of the radiation lambda divided by the diameter of the satellite dish A. So to minimize the spreading, we need as short a wavelength of radiation as possible, or as large a diameter dish as possible. This spreading produces what is known as the satellite's footprint, the area of the Earth's surface over which the energy emitted by the satellite is spread. The bigger the dish diameter, the smaller the footprint, and so the more concentrated the energy will be. Now to look at how we would calculate the footprint of a 2-meter diameter satellite transmitting from a height of 35,800 kilometers at a frequency of 4 GHz, the lowest frequency used and therefore the largest wavelength. Well, wavelength, lambda, is equal to the speed of light in a vacuum c divided by the frequency of the radiation f. Putting the numbers in, this is c is 3 times 10 to the 8 meters per second over the frequency of 4 GHz, 4 times 10 to the 9 Hertz. Must convert everything into SI units at the calculation stage. This gives us a wavelength of 0.075 meters. Now, using the equation shown earlier that sine theta is equal to wavelength over dish diameter A, putting the numbers in, this is 0.075 meters that we found here over dish diameter 2 meters that is given in the question. This gives sine theta of 0.0375 and therefore theta of 2.15 degrees. Now to draw a simple diagram to help visualize the situation. The satellite would be here. This then is the Earth. Angle theta, the angle of spreading. This distance will be 35,800 times 10 to the 3 meters. I've converted to SI units at this stage from the figure in the question given in kilometers. Because theta is small and actually less than 5 degrees, we can assume that the hypotenuse and the opposite are effectively the same length of 35,800 times 10 to the 3 meters. This then, our opposite side, is the radius of the footprint. Rearranging the equation sine theta equals opposite over hypotenuse gives us opposite equals hypotenuse times sine theta, or 35,800 times 10 to the 3 meters times sine theta. Putting in the value for sine theta, this is 35,800 times 10 to the 3 times 0.0375 that we found up here. This gives a value of the radius of the footprint of 1342500 meters. To find the area of the footprint, we use the equation for the area of a circle, pi r squared, where this is our r, our radius. This is pi times 1342500 squared, a figure of 5.66 times 10 to the 12 square meters. Quite a large area. Now to look at the receiving side of things. Well, the bigger the receiving dish, the more energy it will collect. As the area of a circle equals pi r squared, or pi d squared over 4, if we double the diameter, it will give 4 times the area, and so 4 times the energy collected, 4 times the strength of signal. Sound waves spread due to diffraction as they leave a loudspeaker in just the same way as microwaves diffract as they leave the satellite transmitter. The amount of diffraction again depends on the wavelength of the sound and on the speaker diameter. But sound consists of a wide range of wavelengths, and therefore the speaker needs to have a range of cone diameters to ensure similar spreading for all frequencies. Here we have a typical speaker with a small speaker cone for the high frequency, short wavelength sounds, a larger cone for the low frequency, long wavelength sounds. Outdoor and concert speakers tend to be shaped like this, so the sound spreads to the sides due to the small horizontal diameter leading to a lot of diffraction. Little energy is lost up and down due to the large vertical diameter, meaning less diffraction in the vertical plane. This means less energy is lost sending sound to the floor or into the sky.